Okay, well, we'll get started now then. So welcome to session 3 of today's proceedings. And we're going to start off with Dan, who's going to be talking about photophysics of non-fullerene acceptors.
Yeah, thank you for the introduction. So for those of you who don't know me, I am Dan. I'm a fifth cohort, fourth year PhD student on the CDT PV, and I'm going to be switching gear a little bit for this session and starting off talking about the photophysics of non-fullerene acceptors. So first question, what are non-fullerene acceptors? So they are a key component in organic photovoltaics, and this is what we have in organic photovoltaic. We have an absorbing layer, which is formed of materials which are carbon-based rather than sort of silicon or inorganic. And usually you need to have two materials. You need to have, sorry, I'm going to have to move out of the way. You have a donor material and an acceptor material. And when they absorb light, you get not free electron and a free hole, which you get in other material, but rather they're bound together in what's called an exciton. And in order to split that exciton and get those charges out, you need to have an interface between two dissimilar materials, which is why you need two materials at what's called a heterojunction. When you form it, you need to have a heterojunction that sort of exists everywhere inside the absorber layer. So what we have is what's called a bulk heterojunction. And this splitting process that I mentioned usually costs you some energy. So in this diagram here, it's this bit or this bit, depending on which of the two materials you excite. And traditionally, this costed quite a lot of energy. But these days, it's not so much of a problem. And it's because of these materials, non-fullerene acceptors, which I will be discussing. So the top non-fullerene acceptor that exists is this molecule called Y6, whose structure is shown here. And it's actually the acceptor in, well, this is actually quite out of date now, but the best organic photovoltaic blend that exists, which has a power conversion efficiency of somewhere just north of 18%, which is pretty good for OPV. And Y6 has quite a unique structure. It's what's called a push-pull molecule. So it has essentially bits which are acceptor-ish, which are more electron poor, and donor regions which are more electron rich. And it's even more unique than most NFAs. So it's actually got another donor unit squeezed in the middle. Most NFAs of the sort of early families, this was all donor. It just had a central donor core. And what sort of inspired all of my recent work was a paper that came out in 2020, which looked at the photophysics of Y6. And essentially, they proposed sort of semi-dissociated exciton, if you like, which they referred to as an intramoiety state. And they said that this was actually an intermediate on the pathway of charge separation. So you can see the hole eventually gets over here to the donor, but it's sort of semi-separated here. The question that I wanted to ask was, well, how bound is this exciton? What is it? Two charges on different molecules, two charges on the same molecule? You know, can we do a little bit better than they managed to do in that paper? But first of all, I need to tell you some more theory. So NFAs, these non-fullerene acceptors, can undergo lots of different sorts of aggregation. But the main one I'm going to be talking to you about today is this A to A type J aggregation, which is pretty ubiquitous in NFAs. And actually, to spoil the surprise on the next slide a little bit, Y6 also has this, what's known as H aggregation. So, and a very nice paper was published quite recently again, which was about the packing of Y6. And to summarize everything on this slide, they have the A to A J aggregation, which is pretty common, but they also have this H aggregation in this pair 3 dimer in the crystal structure. That will be important very shortly. So, to summarize then, my motivation and the questions I wanted to answer was, you know, can we really structure and the nature of this intramoiety state? How does this compare to other NFAs in different families? And that I will also answer to. can we really understand the photophysics of this material? So we always start with photophysics with the most simple experiment, which you can do, which is the steady state solution measurement. So yeah, that's just the structure of Y6, slightly larger for you there. So I did this in toluene solution, and you can see it's quite a nice. You can see why this material is a nice absorber of solar energy. It's got a peak at about 770, and in the solution, I'll just like to point out these quite nicely defined what we call vibronic features, which are due to the coupling of the vibrations of the molecule with the absorption. Solar cell with materials in the solid state. So these are absorption spectra of Y6 in the solid state from 100%, so just a pristine film of Y6, diluted then in a solid host, which is MCBP, which if anyone knows about OLEDs, you'll probably be familiar with that host. And the key thing to see here is that as you increase the dilution, so you dilute it more, well, clearly the absorption goes down, but more importantly, the absorption starts to blue shift, and this is very characteristic of J aggregates. So from the theory of aggregation, not only does it blue shift, but we also start to see, although it's admittedly a bit difficult from this distance, the return of some of the vibronic structure that I pointed out to you in the solution spectrum. So what I'm showing you here then is that diluting it in the solid state recovers what you had in solution. Certainly something interesting is happening when you put Y6 molecules together. They are talking to one another. They know about the existence of nearby Y6 molecules. Then our technique of choice for actually looking at transient photophysics is a technique called transient absorption. So what we're doing with that is we're firing very, very short monochromatic laser pulse at the sample, creating lots of excited states. And then sometime later on, we hit it with a white light pulse and we see the absorption of those excited states in brief. And so just to run you through what we're looking at here, signals that are negative, so here, 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 and here, those are absorptions of the excited states. And the positive features in the spectrum are absorptions of the ground state. And so the ground state, as we saw in the steady state spectrum, is blue shifted in the 2-weight percent compared to the 100-weight percent. But really, the significant feature on this slide is actually the kinetics. So what I'm doing there is I'm taking a kinetic through here, through here, through here, and through here. So these slices through the spectrum along the time axis. And you can see in the 2-weight percent that the kinetics all overlap with one another. There's not anything particularly exciting happening. You're just forming excited state species and then they're just decaying away to the ground state. In the 100-weight percent, something else is happening. The purple and the green trace, which is this area here, this excited state, this area here, we have this very, very fast sub-picosecond. Now, this was also seen in the previous paper. Assigned it to the formation of this intramoiety state, this slightly delocalized exciton. We also see that here, and we think that actually, well, I won't go on to spoil the surprise, but yes, we also see what they saw. Different NFA molecule that just has a donor-only core, so it's this molecule here called IICO. It's the steady state spectrum first. So you can see I did the same process, so I diluted it in MCBP. You can see that actually the blue shift upon dilution is very small, significantly smaller than the Y6. So in this case, the Y6 molecules don't particularly care whether they're diluted or not. There doesn't seem to be any significant aggregation. Actually, we then did the transient photophysics, and this is also seen here. So actually, I haven't labeled them, but that's sort of deliberate. This is the 2-weight percent. This is the 100-weight percent. Admittedly, there's a little bit of a blue shift between the ground state absorptions there, but all the kinetics, which I haven't shown on this slide, are the same between the two of them. So we have one molecule Y6, which it really matters what the environment of the Y6 molecules, what environment they find themselves in, compared to the IEICO, where it doesn't particularly care, it performs the same. So the question is then, why is there a difference between the two of them? So we also did some more transient absorption, this time quite deep into the IR, and we located this particular excited state absorption. And we also did, collaborators in Würzburg also did some PL detecting magnetic resonance. So I don't want to dwell too long on that technique, it's a bit complicated. But basically, in both cases, we see a feature in the spectrum. So in the PLDMR, we see this positive feature here, and in the transient absorption, we see this feature here, which are not present in the equivalent spectra of IEICO. No, there is only this negative feature, there is not this positive. Positive feature, and the equivalent transient absorption spectrum of IEICO has no feature here. So very definitely, we have an excited state which exists in the Y6 and not in the IEICO. And the kinetic here isn't particularly well resolved in the sub-picosecond region, but I think you can probably it rises up a little bit here. So this species, we can say, is being formed completely by about 3 picoseconds. What is our proposed model to explain all of this then? So I'll start on the right-hand side. So what we think is the true nature of this, what they call intermoiety state, I'll call intermolecular CT state, is really a delocalization of the holes within a Y6 dimer. So the hole is delocalized across 2 molecules here, and that is what is giving rise to these transitions. And furthermore, we can assign these particular excited states to hole-centered transitions on the core, which you may have spotted were not shared by IEICO and Y6. And we assign these ones where we see the same transition in both Y6 and IEICO at pretty much the same place, about 550. Assign that to sort of N group centered conditions. So I should stress this is really a working model. We've got quite a lot of theory going on concurrently with this, which will hopefully either prove or disprove what our hypotheses are. But that's what we're working on at the moment. So yeah, the conclusions then. Well, so the original paper showed that the reason why these inter-CT states are important is because they're intermediates on the pathway to the formation of free charges, which is what we're interested in a solar cell. And that really these aggregation effects have a really dominant governing role in the photophysics. We need to they arise from specifically nearest neighbor core-core interaction. So that's how we've improved. Future work then is to look at what the effects of the morphology of the film are on the behavior of the CT states, which we think is going to be pretty significant. The effect of chemical structure, which is basically a way of changing the electronic structure on the inter-CT state behavior, which you've already sort of shown a little bit. We've shown that, well, if you change the core completely, you get rid of those states. So we already have a benchmark for what we think is going to happen there. And then, as I said, yes, theoretical treatments of all of the above, exclamation mark, which could be quite significant. These molecules are quite difficult to model theoretically, but we're so yeah, just to finish off then, to acknowledge, so the PLDMR data was taken by Janine and Andreas, so they're collaborators at the University of Würzburg. So we thank them very much for that. And then my colleagues in the optoelectronics group at Cambridge, so Dr. Alex Gillett, so he really was the day-to-day supervisor for me on this project, and he's a really and then my supervisor, Neil Greenham. And yeah, with 20 seconds to spare, thank you also for your attention, and open myself up to any questions.
I'll try and make it quick because you've got others. But when you've got the holes delocalizing, do you think they can escape then to, I mean, that's the point, you've got to have the whole thing, the dissociation of the extent.
Yes, so the NFA is actually when you put it together with a polymer to make the OPB bulk heterojunction, it's actually the acceptor. So it's really the electrons that are the most mobile. Having said that, people have made single component cells to sort of investigate this idea, and yes, you can make a sort of like 1% efficient cell out of just Y6.
Yeah, exactly.
So I think the holes and Y6, one of the great things about it is that it does have fairly good ambipolar charge transport. So I think the holes can move fairly well.
Yeah,
yes.
yeah, very intriguing.
Yeah, so it's interesting. They're very interesting molecules for sure. Yeah.
Yeah, thank you, Dan, for the excellent talk. I have a question regarding the vibronic levels that you see in your optical spectra. They look like really nice Frank Condon type series.
Yeah, this spectrum.
Yeah, exactly. Do you know why they disappear? Like, what's the effect causing them to disappear if you change the concentration? On the next slide.
Yes. Okay. So that's a very good question. Yes, we need the next slide, don't we? So, so I think the kind of the classical Kasher model of H and J aggregates, which I alluded to, I think is perhaps a bit deficient when looking at these molecules because of the nature of them, a sort of acceptor, donor, acceptor, quite a strong quadrupole moment. And then there's a whole extra level of theory about thinking about the aggregates of things with quadrupole moments. I think the short answer to your question is I think you basically by the molecules aggregating together, I think you wash out the effects of the intramolecular modes, basically.
Yeah, that's what it looks like for sure. Yeah.
Yeah, I think basically what the molecule-molecule interactions that then dominate, I think, rather than the coupling to the intramolecular. It's something I'm thinking about at the moment. Yes.
Yeah. We tried doing some. Sorry to ask another question. We tried doing some Raman spectroscopy on that.
Yeah. So I've done Raman on the 100% film. Yeah. What you get is well, first of all, you have a bit of a problem because these molecules absorb pretty much everywhere where you have where most Raman spectrometers have lasers. So the best you can do, so our Raman spectrometer will do 405, 532, and 785. But even at 405, you've still got a bit of absorption. So the first thing is you get a massive fluorescence background. So it's quite tricky. Do non-resonant Raman very easily. So what dominates the spectrum is the modes that give rise to this. So you have massive enhancement of CC stretches, basically. But yes, so I did it, but it wasn't particularly informative.
Okay. Thank you. Thank you.
Yeah.
Any more? We might have time for one more quick one if you do. No? Okay. Thank you very much.
Laura, hey everybody. So I'm Adam. I'm going to be talking about the degradation of perovskites in a human atmosphere, and I investigated this using time-of-flight resonance in small-angle neutron scatter. So if you remember nothing else today, this is I'm just going to summarize what I did. I investigated the degradation. I found that, well, as we'd expect, well, at least those of us in TV would expect, improved its resilience to moisture, and it also reduced. Additionally, I also found that the degradation rate seemed to be quicker in the bulk than at the surface, and we'll get onto that sooner. So I did the experiment at ISIS using SANS 2D, and this bespoke. Let's get into it. My research group helped me in doing the experiment. There you can see Alan, Gabriel, Francesco, and basically we use concentrates. Where we had a contrast that would allow us to follow the benefit of using SANS 2D was the very high flux because we're doing time-sensitive measurements, as well as a wide Q range, which allowed us to look at a broad sort of mesoscale features, while also looking at the phase evolution. So now I'm going to briefly explain some of the theory behind my. So using time of flight, grazing incident small angle neutron scattering, typically you use a low incident angle below the crystal. And this ensures that you can get surface sensitivity. Alternatively, you can go above the critical angle and you get bulk sensitivity. The advantage of using time of flight with this is that you can, if you optimize around that incident angle, say you're looking at, you're looking below, you have surface sensitivity, but you want to look at both the surface and maybe a little bit of the bulk. You can basically optimize around that incident angle by using a wave band instead of a single wavelength, and then choose the wave band which suits your needs, basically. And you, after this, you can pull out large quantities of data, which allow you to look at bulk. So this is just a sort of artistic rendition because we didn't have raw scattering data, but to give you an idea of what the output, the raw output looks like. Typically, it'll be split by the horizon, below which you basically have scattering from the transmitted beam directly. And that can be further split into a horizontal component in the QY and a vertical component in the QZ. Your vertical integration can be used to look at phases in the film. So you can either use a bulk cut, let's say a bulk vertical cut, look at sort of layers in the film, so like that. If you at certain angles, or you can just look at the surface, and using that, I could actually look at the specific. Summarize. What? Newest version. Oh well, we'll just continue. So we'll move on to my results then. Unfortunately. I plotted my results. This is looking at vertical cuts. I plotted these vertical cuts using Crackley plots because that allows me particles. And this is just sort of a summary kind of overview of the different chemistries I looked at. So MAPI is your sort of like aristotype. And or other cations, so formamidinium or cesium, and these typically improve the perovskites properties optically as well as in terms of stability because they have lower pH, they have better sizes, they have structural bonding between the lead, the iodine, etc. Quite unstable. So I mean, unsurprisingly, it's quite unstable. It's dominated by a deuterated monohydrate at the first measurement. So that's the green profile at 0 hours. And then after that, you see the production of dideuterated MAPI and lead iodide. In contrast, the other films show, at least the FAMAX and the FASIX films show segregation into FAPI as the initial perovskite. And you also have production. In contrast, the cesium FAMAX film doesn't show the segregation. But you do have a slight production of deuterates shown by the little shoulder on the right. So I'm just going to go into this in a bit more detail, hopefully. So the workflow for determining what phases were present was as so. For the specific phases I'm looking for. I'll then calculate the critical angle and the Q values associated with that, and then I'll compare the theoretical Q or critical Q value for those phases to the peaks I see in my diagram. And so while you'll see in a lot of the films, there's a lot of overlap, or at least the peaks are quite closely spaced, I can still sort of assign phases to the film because the overlap of those peaks results in convolution that increases the amplitude as observed in the profile. And so after 12 hours, that increase in intensity or IQ squared isn't because it's more ordered, it's because you've got this MAPI deuterate, MAPI dihydrate, lead iodide all occurring quite close to each other. So yeah, it's important to note that these films were made under ambient conditions, no antisolvent. It's not necessarily representative of films which would be used in actual devices where typically these things are avoided. And so if we look at the horizontal cut, as I was before, we're now looking at mesoscale scattering features. You can take a bulk cut through the film. And so basically we're looking through the entire film thickness and we see a decrease. Oh, so I modeled this using SAS view. We see a decrease in the characteristics to the size of the particles themselves. But it relates to perhaps the intergranular spacing, the actual mass moment of the particles. So that decrease is quite huge, and you'll see later that this is significantly reduced in the dope samples, or the alloy samples rather. And if you look you look at the SEM images of this as well. This shows you MAPI after degradation in the moist atmosphere. You've kind of got these branches which are fragmented. And by analyzing images like this using a program called ImageJ, I could look at the distribution of particle sizes before and after exposure. So before exposure, you've got quite a broad distribution of particle sizes with some as large as 80 micrometers or 90 micrometers. But afterwards, it's massively small particles below 20 micrometers. And I've had to plot it on a log scale because it's completely dominated by these very, very small particles. So if you look at the alloy samples now instead, you can see the second this, however, it's massively reduced in the sample where we remove the methyl ammonium component, and instead we're just using formamidinium and cesium. Some deuteration in these, but it's not as obvious as in the MAPI samples, which is it relates to these small shoulders on the right peaks on the right peaks. However, you also see the production of potential is cesium byproduct, cesium, lead, iodobromide, or whatever it's. And this has actually been previously identified by other researchers. Again, that wasn't the news version for some reason. So if we look at the SEM of these films, they have quite similar degradation profiles. So the morphology before they look quite distinct, but afterwards they look quite distinct. The effect of the reducing the average particle size. It's not as bad as in MAPI, and this is really shown quite well by when you look at the bulk cuts, the bulk horizontal cuts at this is 8 angstrom. In the phallic sample, it's only reduced by -250 angstroms. That characteristic. In the phasic sample, it's only 150 angstroms in comparison to the -1,000 angstroms in the MAPI sample. Looking at the particle size distributions, the diameter of the phallic sample, again, is quite broad before, and there's massive skew to the left. And here I actually compared directly the phasic sample to the phallic sample. And you can see that the cesium-containing sample retains some of those larger grains, suggesting that it's slightly more resistant to fragmentation. So the last sample I used, the triple cation, this is often used as a sort of, it basically was once it gave you good stability, good optical properties. However, I'm limited in this data set because I did not collect the horizontal cut 8 angstroms. But we can still look at the SEM and look at the particle distribution sizes. So you see in the vertical cut, you don't have phase segregation. You do have a small production of a deuterated phase. But interestingly, it doesn't show the same increase in intensity that I was discussing earlier, which arises from the overlap of phases. Instead, it seems to go up and down and up again, and then down again. And it does seem clear that this attempt to stabilize the structure doesn't completely alleviate that problem. So in summary, our experiment demonstrates that alloying with multiple cations on the A site, as well as bromine on the as in the halide site, does mitigate segregation to some degree, as well as reduce its vulnerability to moisture. However, this isn't you'll need other methods to reduce grain boundary mobility and but I think most importantly, I think this demonstrates top GSANs as a really powerful technique for investigating perovskites, particularly ones containing organic. Apologies, there was more and more slides, for some reason they're not.
So thank you again, that was an interesting talk. Do you have any theories as to why? So you have your triple cation mixed anion cell and it is more stable, and that's what people see as well when they measure those cells. What's your best theory as to kind of what's happening, why those are more stable?
More stable to moisture, right? Yeah.
Well, to moisture and segregation, and
right.
It's yeah.
Well, that is that stabilizing the perovskite cell with cesium formamidinium improves the cubic factor. Reduce the bond between lead and iodine, which again decreases. So I think it's a less reactive. Basically, reduces the rate of degradation.
No, I mean, if you calculate the tolerance factors, once you get into these multiple anion cation systems, they're not as obvious as you might think. They don't kind of, it doesn't go that cubic, I would have thought.
Well, yeah, I mean, it is better than MAPI, at least.
Sure.
Yeah.
Yeah, I mean, I'm genuinely interested because we find exactly when we have these triple cation mixed anion cells, like activation energy for ion motion goes through the roof. It's higher than anything we've measured on any other component systems. And it's kind of what it is about that mixed anion cation system in particular that is just so much more stable. It's an interesting question. I'm not sure I know the answer to, but yeah. Thank you.
That was a really, really nice talk. My question is just about, so 75% humidity seems fairly aggressive. Do you expect a cell to actually operate under those conditions, or?
So I use such a high humidity to accelerate the process, basically.
I see.
But yeah, you wouldn't expect it. Ambient conditions be more.
Okay, sure. Yeah, no, I was wondering because it's like unless you actually like break your encapsulation and spray some water on it, I wouldn't expect it to get anywhere near that high. But yeah, it makes sense. You haven't got all the time in the world in the instrument, so yeah, no, it seems.
I mean, that's part of why I didn't have. I was limited in the data set on that cesium.
Thanks. No, thank you very much.
Any more questions? No, thank you very much.
Afternoon, everyone. So I'm going to be talking about the electronic structure of Al04- and ethylene doxythiophene or PDOT, sponsored by a mixture of EBSERC and Lloyd's Register. So the entirety of my PhD is actually focused on these single chains of PDOT with these anions coming in. Now, the original motivation of this was a battery with an aluminium anode, motivated by the benefits of aluminium, which have never. However, one of the first things that I discovered was actually that these anions have a real strong energy well effect in these locations along the polymer backbone. Obviously not what you want in a battery cathode. When you're trying to put a charge carrier through the bulk of an electrode, what you're looking for is a really nice flat profile of energies of all the locations of the anion as they make their way through the electrode. This highly localized energy system then creates high levels of hysteresis and quite a bad energy efficiency, which is seen on when you actually try and produce this thing as a battery. That's really driven this research down a more sort of conducting polymer theory route. You do see PDOT in supercapacitors, and then you can see actually that you can imagine a tangled mass of PDOT with a high surface area. And this redox reaction then works really well because you're not actually trying to drag the charge carriers through the bulk of the electrode. What I've done here is all the work here is powered by hybrid DFT. It's the most common method used these days, produces really good results across a wide range of materials, and has also been shown to be highly applicable to this system. Interestingly, the challenges that you get when you're trying to model PDOT as opposed to, say, for example, a more conventional battery electrode or crystalline material is this highly conformal chain. This creates a complete configurational nightmare in trying to find energy minima, because these things can adapt and there's lots and lots of positions that they can end up in. And so trying to find one in which to base your calculations is difficult, and much of the pre-work to this particular piece of research was trying to work out just how much that matters and what the dominant effects and the not so dominant effects. It turns out the actual positions of the anions, the most dominant effect, and the minor deviations in geometry are not so important, which allows you to sort of do this work without having to carry out thousands of calculations for every single arrangement of anions. Now, conducting polymers are characterized by having a conjugated carbon backbone, which is this carbon backbone that runs all the way through the polymer. Now, carbon obviously has a valence of 4, so it can bond with up to 4 other atoms. Here, each carbon is only bonded to 3 other atoms, which means you've got a spare electron. That gets consumed as a sort of single double bond. So every carbon has 1 single bond and 1 double bond attached to it. Now, conventionally, they sit in if the PDOT is undoped and the use of doping is not sort of technically correct, but it's become completely accepted, that's come from inorganic semiconductors. Then they sit in one particular orientation, as you bring, which I'll show you in a minute. And as the anions come in, they create this localized distortion, which is a few monomer units long. Now, initial theory, conducting polymers were only actually discovered in around 1980, leading to a Nobel Prize for the 3 scientists that discovered them. Since then, they created a whole body of research, and other pioneers in the field created a body of research trying to explain some very interesting sort of electronic and optical properties. And one of the things they actually theorized from their experimental results and from early computational methods such as one-electron theories and semi-empirical methods, which are all that were affordable computationally at the time, was that as you bring in this one anion, it creates this structural distortion along the polymer backbone. But then as you introduce another one, that there would actually be an energy driver for the 2 anions to co-locate despite the coulombic repulsion between them. Now, there was a lot of evidence behind this in terms of this model seemed to fit really well, that had some sort of glaring errors in it that got overlooked at the time because it was the best model that could be produced. And the interesting thing is this model gained so much traction that even though modern computational methods have actually sort of moved on from it, it still features and still influences people's interpretations of conducting polymers to this day. And so what my research is actually doing is applying the conventional method to a novel system to add to the body of research, trying to move that theory on. Right, this is originally an attempt to do a 1-slide presentation, which has been an aspiration of mine since the first time I saw someone do it. However, I clearly failed because I've got 5 slides, but I'll spend most of my time on this one. This contains nearly all the information that you could actually get out of the system using the methods I've been using. I'll go through it one step at a time. So generally in the background, ignoring everything else, you have a band structure graph. I've shown a few layers, a few energy states either side of the HOMO-LUMO gap, highest occupied molecular orbitals and lowest unoccupied molecular orbitals. I've then put the molecular orbital graphs for the 3 states either side of the gap, and I've indicated the up and down spin electrons for the highest occupied levels, and where you have a singly occupied level, I've also shown the one below. Everything below that is occupied, everything above it unoccupied. Should be fairly self-evident. You've got a 6 p dot system throughout, but what I've done is I've introduced 1 anion, 2 anions, 3 anions, and as you've gone through, I've picked the energy, you can have multiple configurations for this number of anions, but I picked the lowest energy one. At the bottom, you have a solid graph, is the bond lengths for the carbon bonds in the monomer unit, and then missing is the carbon bond joining the monomer units together. And the dash graphs are the charge concentration, the atomic partial charges summed over the monomer units for each monomer unit, showing overall how the charge concentrates over the length of the polymer. For the undoped system, you can see that the bond lengths, the middle bond of each monomer unit is long. So that's the single bond. It's only got 1 electron in that bond, and as a result, the bond is slightly longer. You have the double bonds either side. The extra electron makes a stronger bond, draws those electrons closer together. When you bring in an anion, what it does is it actually inverts the bond structure there. This is all so far completely conventional. They knew this right at the start. When you bring in 2 anions, you get a much more powerful bond length inversion in the middle. 3 anions, you get even more so. It's now more widespread. And 4 anions, you've actually got almost this slightly strange behavior in the middle. Now, it's really important that the anions don't want to sit over the ends. There's a number of reasons for this, which we won't go into. Basically, they can't sit there. And one of the fundamental things that I'm showing with my work is actually that the apparent driver for the anions to sit together is not so much driven by some force that makes it preferable for them to do that, but simply that they can't sit over the ends. So they have to force themselves together, and that's what drives these anions to sit together. And you can clearly see the Coulombic repulsion building up between the anions because it's driven up the orbitals on the anion, so they actually start featuring in the states around the gap. What am I doing for time? Good. Now, so that's point number 1 against the bipolar model, is that the driver for them to sit together is caused by the end effects rather than by any driver for them to actually sit together. Now, when the original researchers first started looking at the spectroscopy and doing this experimentally, they noticed that when you took out 1 electron, you ended up with this sort of extra, what looked like an extra state here and very clearly sort of an extra state here. And then if you took out an extra electron, the band structure changed again, and there was sort of extra state here. Now they theorized that as you bring in an anion, you introduced a bonding and an anti-bonding state that would appear in the gap. Now, when you introduce the anion, it does indeed introduce an anti-bonding and a bonding state. But what this shows is that actually that's not driven by the anionic anti-bonding bonding state. In fact, these happen up here and down here, and I'll show you that on the next slide as the last slide of the presentation. What you're actually getting is that as you remove an electron, it actually bumps up this now unoccupied state into the gap, creating the sense of a new state without it actually being a new state. As you remove the second electron, it bumps the level wholesale up into the gap, and this process is repeated the more electrons you remove. Because these electrons are mobile across the system, there is a preference for the electrons to pair. So if you actually look at the system as a whole, you tend to end up with paired electrons once the system's actually reached equilibrium. It is possible to build up a spin concentration as you charge this system. So that's point number 2 against the bipolar model. So in fact, what you've actually got is really quite a conventional system where as you remove electrons, you just move down to the next state and you're not creating new states. The closest you get to seeing the new states is you get to see the non-bonding orbitals of the anions starting to feature around the gap when the concentration of anions builds up enough to push those states up to push those orbitals up towards the gap. Finally, you can see from the charge graphs, you can see how the negative charge starts to build up. This is the positive. This is the charge on the P dot backbone, and so it gets more positive the more anions are there, because the anions are drawing the charge out of the P dot, creating a positive area along the P dot backbone. Okay, and finally, just to prove the previous point, these anions, you can see how much of a gap there is between the bonding and the anti-bonding orbitals. So the anti-bonding orbitals are a full 9.2 electron volts higher than the bonding orbitals. The area we're interested in here is about 3 electron volts in the undoped state, and coming down to closer to about 1.5 at the sort of fully doped state there. You do have 8 of these in the middle, which are what you can start to see featuring here, for example. Okay, so this work, as I was saying, this fits into the overall picture. These conclusions aren't drastically new. The power of the end effects, I believe, is more novel in terms of making that really clear. But generally speaking, it's a conventional approach to applied to a novel system. Now sort of adding to that general sort of body of research, moving away from the bipolar model to a way of understanding these polymers that's more up to date. Thank you very much.
Oh, any questions?
It's quite intriguing what you're saying, but what's the kind of outcome? In a sense, are you saying that the charges do move along the polymer because they pair up by, as you say, it's not a bipolar, but still, do they effectively pair up? Does that mean you get good charge transport along the polymer?
Oh yeah, okay. So the charge transport, that's and do you mean in terms of electronic conduction?
Yeah, yes, I guess I am, or ion conduction, or both. I mean,
So well, so it's interesting. The two are completely separate, right?
Yeah,
so when you're actually conducting electricity down the polymer, you don't per se get any anionic movement.
Right.
So what the anions do is they introduce these defects, and these defects then overlap slightly. And by the main thing is that the more anions that you add, the band gap gets narrower, and that's what really allows the conduction to take place. You can have much easier promotion of the electrons into the otherwise unoccupied level. That's what allows the conduction. Then you get it's mostly by whole conduction actually. But so the higher concentration of anions then leads to much more overlaps of those defects, and it's those that the defects themselves travel down the chain. So you get that's by resonance. So those single double bonds, they alternate so easily that they alternate with conduction, but the anions don't move.
Okay.
So yeah, it sort of like ripples. They ripple down the backbone, if you like, by conduction of holes.
Right. But sorry, this is a battery material, so aren't you supposed to be conducting the ions?
Well, that's it. This is why this has gone more theoretical, is because the resistance the anions to moving was one of the first discoveries. Now you could use this as a springboard to saying, for example, future work could be try and identify materials in the backbone that had much less energy well effect. That's not the route I've gone down, because actually it turns out the conducting polymer community will definitely be interested in this work, whereas the battery community, there's only a possibility they may be interested in this work. So in the interests of maximizing sites, that's the route I've gone.
Yeah, thank you for the great talk. I'm just wondering, have you ever thought about replacing the P dot backbone with a carbon nanotube? Because it's exactly how what you describe is exactly how a doping carbon nanotubes works. So I was just wondering that.
No, I hadn't thought about that at all, actually. my head immediately jumps to how many extra atoms that would add to the system and how slow the computations would then be. But no, that's actually a really interesting idea. Could scope that out for.
Yeah, I'll talk to you later about it. I'm just very excited about Carbon nanotubes. So I think maybe the audience isn't.
Absolutely.
Hi, yeah, thank you very much for a wonderful talk. It was nice to see some other organics. I was a bit worried I wouldn't see any, but it was nice to see some. So my question was about the end effects that you mentioned. So am I right in saying your model was just on this hexamer? So I can see how the end effects would be really significant when you're only modeling 6, but are they going to be as significant when you're thinking about a whole polymer chain of 10, 100,000 monomer units?
Well, that's the interesting thing, right? So you don't actually have a good number for exactly how long the chain units are in the cathode, but you're talking well under 100. And realistically,
sure, fine, okay.
There could be, it's most likely considerably under 60 and probably under 30. So they do still play a role. It is true that as you get longer, the end effects do get less important, and that's a critical effect. And reason for this work focusing on chains that are this long is it does have a lot to do with computational resource. And the n-cubed effect of adding extra atoms, you do quite quickly bang up against that, even using modern supercomputers and modern methods.
Sure. No, thank you very much. Thanks.
Okay, thank you very much.
That brings us to the end of today's session. Thank you to everyone who has presented throughout the day. That includes myself, so it's a bit weird to say, but all really interesting talks on a really wide variety of topics. So really illustrating the benefit of bringing these 3 CDTs together. A couple of housekeeping points before we go. If you can keep your name tags with you and bring them back tomorrow, rather than leaving them outside. The social event this evening will be at Cubana in Leopold Square. If you get there between 7 and 7:30, that'd be ideal. And straight after this, some of us are going to the next street along to the Red Deer for a couple of refreshments. So if you'd like to join us there, then you're more than welcome. Thank you very much.